including the presidency of the British History of Mathematics Society. Am I getting that right? It's British Society for the History of Mathematics. I think that's what it is. That's right. That's the main body, academic learned society that deals with history of mathematics. She is a speaker that's very, very much in demand for many reasons, but especially because of a book that came out last year, was it?
Yeah, well, earlier this year, April.
Earlier this year, that's right, yeah. Called Once Upon a Prime, where she investigates exactly these things, beautiful links between literature and mathematics. And I've heard many people gush about the book in many ways, including comments that they never realized that Moby Dick was book mathematics. So Stephen Levitt, for example, many of you know him as author of this book, Economics. He described it in the New York Times as an absolute joy to read. And just to give you a flavor of what a special occasion this is, it's very hard to get Sarah as a speaker. She's appeared on Economics podcast twice, I think. She's appeared on Radio 4, or maybe Channel 4 TV as well. I don't, yeah, that's right. Just recently, for example, I guess it was last week, she was at a conference in Glen Eagles with the other speakers were Neil Ferguson and Ian Rankin. So you can see how hard it is to get Sarah as a speaker. It's a humble institution like we have here. And I think greatly looking forward to what we have to hear. So thanks, Sarah.
Thank you so much for inviting me. It's lovely to be here. Edinburgh is such a beautiful city. I don't know. I've been built up quite a lot here, so you know, it hopes up too much. So I want to talk this evening about the beautiful links between literature and mathematics. And okay, not too much specifically Christmassy, but just we're going to have a good time and have a bit of fun, all right? But we've got to begin by saying we do not often see these words linked together, right? Literature and mathematics tend to be put unfairly, I hope to convince you, into separate boxes. In our minds, we think of them as being almost not connected at all. But this is not the case. So why do we even think this? Why do we think they're not connected? Well, it's because in our minds, perhaps not in the minds of the people here, but in the general conception, mathematics is put with science. We say that mathematics is the language of science, and that's completely true, of course. The reason is that the universe is full of structure and pattern and symmetry, and all of those lovely things are best described and understood using the language of mathematics. So that's why mathematics is so vital for science. But of course, we are all creatures of the universe. We enjoy structure and pattern and symmetry. And so it's going to emerge in our creative forms of expression, whether that's in music, in the rhythms and patterns of music, or in beautiful symmetry of works of art, or in literature, right? It's going to come out. And if we want to find the mathematics in literature, well, where could we start? Where might structure and pattern be most close to the surface, most clear in literature? Let's start there with poetry. So it's notoriously difficult to define poetry. I challenge you to do this. I actually looked up poem or poetry in my dictionary, thinking, well, I can't do this, but dictionaries are supposed to be good at that sort of thing. I looked it up and it said it's written in verse as opposed to prose. So I was like, okay, well, what's verse then? And it said verse is a kind of poetry. So thanks a lot, dictionary. That was no help at all. But you have an answer here.
Not my answer, but text with crooked right margins.
Text with crooked right margins. That's a good one. So, I mean, there's some kind of structure to a poem, whether that's line breaks, as a nice way of expressing it there, or perhaps there's a rhyme scheme with different lines specified that are rhyming with each other, like something like a sonnet has a particular rhyme scheme to it, or perhaps the precise numerical constraints of various forms of Japanese poetry, like haiku, probably most famously, with its precisely 17 sounds or syllables. there is always some sort of constraint. And when there's a constraint, that means there's a structure. And when there's a structure, there is mathematics. So I want to give you just one example of a particular kind of constraint that has led to some mathematics and some kinds of mathematical ideas that were first encountered and developed in the context of poetry. Hundreds of years before, perhaps we might think of them having been developed. And that's the rhythm of poetry, the meter. So here are some questions you might ask about poetic meter. So meter is like the patterns of stressed and unstressed syllables or sounds. So in Western poetry, we have things like, you know, iambic pentameters, right? Dee-dum, 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 dee-dum. It's not very poetical, but if you analyze a bit of Shakespeare, you will find this, this particular pattern of stressed and unstressed syllables cropping up over and over again. In Sanskrit poetry, we talk of light and heavy syllables, lagu and guru syllables, and we might ask some questions. I'm just noticing here, I hope that this hasn't happened throughout, but this is supposed to be gradually revealed as I speak, but it hasn't happened. So if all my surprises are ruined in this talk, I do apologize right now. Anyway, we're supposed to have this, we're asking about how many ways are there to create feet, right? So patterns of a particular number of syllables with a particular pattern of heavy and light syllables in there. So do we have, for example, if you had a foot that had 2 syllables, you could have 4 patterns. It could be light, light, or light, heavy, or heavy, light, or heavy, heavy, right? And so if there's 2 choices for every syllable, then it doesn't take us long to realize that the answer, the total number of syllables of a particular length with, say, n syllables in, will be 2 to the power n. It's a power of 2. Because you've got 2 choices for every syllable in your foot. So you can work that out. And this was being done like 2,000 years ago. There's an Indian mathematician called Pingala who wrote a sutra about poetry, and this powers of 2 in terms of the number of feet of a given length was discussed. You can refine your question. You can ask, okay, I want to know about how many feet are possible that have 7 syllables, but 3 of them are heavy, for example. So that question is, how many of my n-syllable lines of poetry have a particular number k, let's say, heavy syllables? And Pingala talks about this diagram, I should immediately say, is not from Pingala. This is much more recent, maybe 1,000 years more recent. Pingala talked about constructing a kind of mountain of numbers. And this is the kind of picture that came with later commentaries on his writing. And you might recognize this as being what we now call, at least in English-speaking countries, we call it Pascal's triangle, which contains, if you're a mathematician, you'll know it contains what are called binomial coefficients. If you look at, say, the rows tell you about n syllables, and the entries in the rows tell you how many possible feet there are with a given number of heavy syllables. So like let's see, the 3rd row and 2nd entry would be 2. That means that there would be of the possible feet with 3 syllables, 2 of them would have 2 heavy syllables, right? So actually, no, that's a 3. Is that a 3? Well, we can work it out later. I can't read my own handwriting. So, so how many of these? That question: how many of these feet that have k heavy syllables? The answer to that is this pyramid of numbers, or this mountain of numbers, which now we call Pascal's triangle. In Iran, I believe it's called Khayyam's triangle, after Omar Khayyam, the poet and mathematician and astronomer. There's a different question we could ask, and that is that these light and heavy syllables have a different duration normally. When you're reciting this poetry, the light ones last, say, a beat, and then the heavy ones are twice as long. So instead of saying how many of these things are there with a particular number of syllables, we might ask how many there are that last a given length of time, how many of a given duration. And that leads us to another mathematical. Yeah, okay. Oh, no, just don't see that yet. Okay, right, so that leads us to another question and another mathematical sequence, not powers of 2 anymore. And so here's what's happening. If we're asking how many of these have duration 1, then there's just one, because you can have just one short syllable. What about duration 2? Well, you can have short, short, lagu, lagu, or one long syllable. When they're looking at length 3, there are 3 things listed here. And so it looks like you're starting your sequence 1, 2, 3. So obviously you're expecting the next number to be 4, but it's 5 actually. There are 5 ways of making a foot that lasts for 4 beats. And those are listed there. And so we're getting this sequence 1, 2, 3, 5, which of course many of us in the room will recognize. Why is it that sequence? Well, if we think about how to make the possible feet that last 5 beats, length 5, what you can do is you can take all the ones of length 4 and then add a short syllable, a lagu syllable at the end. Or you can take all the ones of length 3 and add a long syllable at the end. So the total number of these will be the number of length 4 patterns plus the number of length 3 patterns. 3 plus 5 is 8. And that's how we can get all of the numbers in this sequence. 5 plus 8 is 13, 8 plus 13 is 21, and so on. So this sequence you probably recognize, we call it the Fibonacci sequence, but hundreds of years before Fibonacci introduced it to Italian audiences in his book at the beginning of the 13th century, it was being used and studied in India to understand the possibilities for Sanskrit poetry. So that's just 2 examples of how looking at the mathematics behind poetry can give us new pieces of mathematics. And I want to come several centuries closer to our time with my other example around poetry. And this is not about meter, it's not about rhyme schemes, it's not about a particular number of syllables in the poem. So if you're not going to have any of those things as your poetic constraint, what can you have? Well, this next example is a poetic form called a sestina. And sestinas are brilliant. It's giving you the first 2 verses here of my favourite sestina by Elizabeth Bishop. It's called A Miracle for Breakfast. A sestina has a very specific structure to it. It doesn't have a rhyme scheme, so lines don't rhyme with other lines. What it has is, looking at the first stanza, those words at the end of the lines in the first stanza, they are going to be the end words in all the other stanzas, but they appear in a different order. They get shuffled every time. And the shuffling is always the same. So you get 6 words, 6 lines in that first stanza, and those 6 words are shuffled in a way I will now describe. So if the words are 1, 2, 3, 4, 5, and 6, what you do is in a kind of lovely corkscrewing pattern. So you start from the end and work backwards, and you interleave with starting from the beginning and working forwards. Right, so the 1, 2, 3, 4, 5, 6 becomes 6, then 1, then 5, then 2, then 4, then 3. So you can see this happening with the original ordering in the first verse: coffee, crumb, balcony, miracle, sun, river. Now becomes, we start at the end, so river, then coffee, then sun, then crumb, then miracle, then balcony, right? And that is the ordering in the second stanza. Okay, so we do that again to make the ordering in the third stanza, and again, and so on. And yeah, I'm anticipating now my lovely slide won't just all show itself at the same time. Okay, there we are. Right. Okay, so that's the original verse. You do this and you do this and you repeat and repeat and repeat. By the 6th verse, this is the ordering of the words. So crumb, miracle, river, sun, balcony, coffee. And a sestina, as you may know, consists of 6 verses, each of 6 lines. So by the time you get to verse 6, you've got to the end of your collection of 6 verses, traditionally, you've then finished with a little kind of tied up with a bow, finished with a little 3-line mini verse that has all of the 6 end words in some order. But if we didn't stop at that point, if after verse 6 we tried to continue with this pattern of shuffling, then the words in verse 7, what do? We start from the end and work backwards, coffee, interleaving with starting from the beginning and working forward. So then crumb, then balcony, then miracle, then sun, then river, yes? So that's the order we would have in our putative seventh verse. If you compare, that's exactly what we started with in the first verse. So actually those 6 verses are the complete iteration of this shuffling process. It's the full thing, and every word in this process, it has appeared at the end of every single line exactly once. And so it's a very beautiful structure. And in those 6 verses, you have the full thing. So I don't know, I often wonder, can we detect this? Like, do we detect subconsciously that we got to the end of the line? And then the next one would bring us back to the beginning? I don't know, but I do like this little structure. So we've seen already how, in early mathematicians in India were studying poetry and looking at the possibilities and what kind of forms you could create in terms of meter. As mathematicians, we can say, interesting sestina, 6 by 6 sort of structure. Would this work for other numbers? So of course, as a mathematician, our favorite number is n. So can we create an n-ina? Well, let's see. And you could see, yeah, all my lovely surprises. So let's imagine if we tried to do this. So what do I mean by an n-ina? So that would be n stanzas, each with n lines, and the end words will be jiggled around according to this process. So if we were to try it for, say, n equals 4, and so I picked 4 words that commonly occur together, north, east, south, west. This shuffling process would give us, to begin with, what do? We start at the end and work backwards, so it would be west, and then from the beginning and work forwards, then north, then south, and then east, right? That'll be the end words in the second stanza. Not looking great, right? Because south has stayed where it is, so it's not ideal, but let's press on. So what happens next? Well, again, same process, start at the end, so east, and then west, and then south, and then north. For the third stanza, okay, south again stays where it is. Let's persevere, even though it's not looking good. What would the fourth stanza look like? Well, again, start at the end and work backwards, so north, and then east, and then south, and then west. And that's a problem, because that's already given us back the first ordering. So that's no good at all. I mean, it completely fails. We only have 3 different verses, and there's one word that stays in the same place all the time. So that's the quartina, which you invent a name for and then immediately dismiss because it doesn't work. It does not work. We can't write a quartina. But But what are there other values we can make? So you can see that there are, because unfortunately all my transitions have collapsed into a black hole. But so there is this really lovely criterion. Now this is sufficient, but is not necessary. In other words, this little rule that I've written down here tells you there are a particular kind of number for which you can make an n-ina, but it doesn't cover all of the possible numbers for which you can make an n-ina. So for example, a sestina, that's n equals 6. That's not any kind of a prime number. So I'm not saying this is all the possibilities, but this gives you a guaranteed set that work. So what kind of collection of numbers is this? Well, they are the Sophie Germain primes. So Sophie Germain was a brilliant French mathematician. She was born in revolutionary Paris, and she studied mathematics kind of initially against her parents' will, that they were so against her doing all this hard thinking that they tried to stop her by not allowing her to have a fire in her room at night so she'd be too cold to study, not allowing her to have too many candles, but she still found a way because mathematics is so exciting. She studied mathematics even at university level, but she had to do it kind of by correspondence, so she couldn't attend lectures or anything, but she studied remotely, as is the fashion nowadays. She used a false name. She pretended to be called Monsieur Leblanc, and she corresponded with many of the leading mathematicians of the day. She did eventually tell them who she, she was a girl, and that they were all fine about it. But yeah, so she studied mathematics because she loved it so much she couldn't, in spite of all the obstacles, that was the thing she wanted to do. And one of the things she was working on, she did lots of brilliant mathematics. One of the things she was working on was trying to prove Fermat's last theorem. That wasn't eventually proved until the 1990s. That's no skin off her nose. The techniques that used to prove it were a long way off being anywhere close to being developed. But she did manage to prove it in some particular cases. So the theorem says, as you probably know, that you can't solve in whole numbers, positive integers, you cannot solve x to the n plus y to the n equals z to the n, where x, y, and z and n are all positive integers, if n is greater than 2. So you can do x squared plus y squared equals z squared all day long, but you can't do x cubed plus y cubed equals z cubed. You can't do x to the n plus y to the n equals z to the n. Now, what she managed to do was to show that for lots of different values of n, this is correct. You can't do it. And some of the values that she did this for were particular prime numbers that we now call Germain primes. So n is a Germain prime, as you can see, if both n and 2n plus 1 are prime. So 3 is a Germain prime because twice 3 plus 1 is 7 prime. 7 is not because twice 7 plus 1 is 15, and that's not prime. So this result tells you, this is a late 20th century result, that if, for example, n is 3, you can use this structure. You can write a tri-Tina. I've seen those in print, some of those. That is possible with this theorem. There is space now for your creativity. Over Christmas, think of a Sophie Germain prime, let's say 23. You can write a 23 Ina. Send them to Mignon here. I'm sure you'll love them. So that
a prize.
Yeah, special prize for doing that. But this, this shows us what can be possible. And it's some nice little bit of mathematics that comes out of thinking about poetry. Yeah.
A copy of Sarah's book.
Yeah, yeah.
Nothing about it. So what about the n Inas that are possible, but where n is not a prime? Is there any story to be told about these n?
There is. It's a bit more complicated than I wanted to go into, but there was a paper written about this about 10 years ago that gave exact criteria. My recollection, without having it in front of me, is that it's about kind of powers of 2 multiplied by one of these primes. Like 6 would fit into that, 3 times 2. But I don't like cut out that bit of the video just in case I'm wrong. I think it's something like that. But yeah. Exercise for the reader, right? So we talked about poetry. I want to talk a bit about structure in other forms of literature, because it's not just in poetry that we find structures. Actually, I think the best way to think about this is not to say, is there a structure, but what structure is there? What choices have we made? And it's a bit like geometry. In geometry, we have this hierarchy: point, line, plane, and keep going up the dimensions. At each point, at each stage, I should say, we can impose rules. In geometry, we call them axioms. We say, if you start Euclid at the beginning, you say, okay, we are told any 2 points will define a line. Any 2 distinct points, or 2 lines that aren't parallel will meet at a single point. So these relationships between points and lines are described. If we tweak those axioms, we get different kinds of geometry. Language itself is built up in a similar way, with similar hierarchy. There are letters. Letters make up words. Words make up sentences. Sentences make up chapters. Chapters make up volumes. At each level, we can choose to impose rules or constraints. So, for example, there have been books written at the level of letters. There have been books written that have a constraint. They do not use a single letter E, for instance. That's the most famous one, La Disparition by Georges Perec. The English translation is called A Void. No letter E's in the whole book. So that's a constraint. But there are, at each level, you can choose what rules or not to impose. And then you get a different structure. And just as within the rules of Euclidean geometry, we can prove Pythagoras' theorem, well, within the rules of the sonnet, we can write, shall I compare thee to a summer's day? So, you know, we can play around, we can play and explore the structure that we have created. So let me show you 2 examples of structures. Now, I really hope this next slide will work. Okay. Okay, I'm going to talk about it for a minute first. So the next one I want to show you is, it's a wonderful book by Eleanor Catton called The Luminaries. This came out 10 years ago. It won the Booker Prize in 2013. It's got everything, this book. It's got everything you could want from a plot. It's got love, betrayal, murder, stolen gold, opium, intrigue, unsolved crimes, everything you could want. And one of the major themes of the book is the interplay between chance and fate and destiny, and how much, to what extent we are in control of the events of our lives, and to what extent we're just being buffeted around by forces that we don't understand. So to tie in with that, there are themes around astrology in the book. So there are, for example, 12 characters, 12 important characters, each of whom is associated loosely with one of the 12 signs of the zodiac. And their actions, their decisions are to some extent determined by the position of the stars in the night sky at the time that the events were set, which is kind of a late 19th century gold rush town in New Zealand. But the mathematical part of the structure I want to talk about is the fact that the book is divided into 12 chapters or sections, and each one is half the length of the one before. Right, so the 12, that links in with this, you know, the astrology theme. By the way, she doesn't necessarily believe in astrology, but she's just using that because it links in with, you know, this discussion of chance and fate. So the 12ness is fitting in with that, but also the halving of the chapters fits in with the waning of the moon, and it all links up very nicely. When you are reading the book, you can feel that something's happening. You might not necessarily pick up it's exactly halving every time, but the effect that it has on you as a reader is really interesting. So let's see what comes up when I press this button. Okay, the whole thing. Right. So I've got this little picture here. This literally shows you visually what is happening. Here's chapter 1, right? Chapter 2 is half the length. Chapter 3 is half that again, half again. That's chapter 4, chapter 5, 6, 7, 8, 9, 10, 11, and 12. Spiraling in towards, well, that point there. I won't say the center. If you on your way home, if you're a mathematician, you might like to work out exactly where this would end up if we carried on to infinity. But this structure that emerges is having the effect of spiraling in onto the end of the book. Now, the chapters are not set, they're not chronological. So the very final chapter, which is just a short conversation between the 2 main characters, the luminaries of the title, that's another astrological reference there, the sun and the moon. So they have a little conversation halfway through the action, but at the end of the book. And by this stage, they don't know it, but you do. They are trapped. Their fate is already sealed, unbeknownst to them, because the spiral has enclosed them, gradually constrained them more and more. And as we read the book, we feel the gears are tightening, the pace is picking up, you know, the chapter's getting shorter and shorter, gives us that impetus, and things are building up and building up and building up. So it's really, really fantastic to experience that when you're reading it. But there's something more we can say about this. I mean, you can see already in this picture something about the length of the book. The first chapter is more than half the whole book, right? You can just see it visually there. And we can use this mathematical constraint to work out actually the whole length of the book just in terms of that very final chapter. Because if we say that that final 12th chapter has a particular length, let's say S for shortest, then the one before that has length twice that, twice S, and then before that 4 times and 8 times and so on and so on and so on, and 11 doublings back we get to the first chapter. So the first chapter, its length is 2 to the power 11 times that shortest length chapter. Now 2 to the power 11 is 2048. So the first chapter here, this is more than 2,000 times as long as that very tiny last chapter. So every single word that Eleanor Catton writes in the last chapter forces her to write over 2,000 words in chapter 1. So that's something to bear in mind. But we can also work out the total length of the book in terms of just that very last chapter. Now, we could just add everything up, 1 plus 2 plus 4 plus 8 and so on. There is a shortcut way of doing this that I might have showed you gradually, but I'm going to show you all in one go. Right, here's the total length of the book, and there's this little nifty trick that you can use to work this out to avoid having to do any actual work, which mathematicians are fond of. So what you do is you write this sum down, you're adding up s, twice s, 4s, and all the way along to 2 to the power 11s, you've got all the chapters added together. Then, seemingly, strangely, make the decision to, instead of actually doing this work, you double everything. And what you find is that you get everything double. So s goes to 2s, 2s goes to 4s, and so on and so on and so on. And that 2 to the power 11 becomes a 2 to the power 12 at the end. And the reason I'm doing this, you can already see, it's because I'm going to subtract the top one here from the bottom one, and loads of stuff will cancel. So on the left-hand side, I'll get 2t minus t, that's t. And on the right-hand side, loads of stuff cancels out. All the 2s's, the 4s's, 8s's, and so on, all of those middle things cancel out. And all I'm left with is 2 to the 12, take away 1, lot of s. So that's the total length of the book without having had to do any actual adding up, which I'm not very good at, so that's a relief. I'm a good mathematician, but I'm not good at arithmetic. So we got 2 to the 12 minus 1 multiplied by s. That's the total length of the book. Now I wanted to show you this because it's a natural question, and a very fair question, to say, look, Sarah, you love mathematics. You are going to look at stuff and see the mathematics in it and want to do the mathematics, and that's lovely, but this is not anything to do with how Eleanor Catton writes it. You know, she's got this structure, that's fine, she's thought of the idea, but she doesn't necessarily know this formula. And, you know, so let's just think about that for a second. Well, I have evidence that she does know this formula. We can see that 2 to the power 12 is fundamental to the structure of the book. Okay? It's part of this formula, and it's very important to the underlying structure. So I mentioned a few minutes ago that the book includes a passage about stolen gold. There's some stolen gold that's important in the book. And there's a court case around this stolen gold in which the exact monetary value of the gold is given. And it's £4,096. That's 2 to the power 12. So if you see that when you're reading the book, you know something that's not a randomly chosen number. It's exactly 2 to the 12. That's vital for the structure. That stolen gold is sewn into the fabric of the book. It's right there. So yes, she does know this, and she hasn't just randomly happened upon it. It's a conscious decision, and it helps us to enjoy the book more, I think, if we spot those things. I'm going to give you another example of a structure in the book, and then we'll talk a bit about the symbolism and metaphor of mathematics that appears in literature. So the next and final example of structure is in a book called Life a User's Manual. And to tell you what the structure is, I'm going to show you this picture. This is a puzzle that was doing the rounds in the parlours of 18th century France. It's a card puzzle. I'm showing you one solution, but there are 1,151 others, so you can find all of those if you like over Christmas. The game is you take the highest 4 cards in each of the 4 suits of a pack of cards. So that's the ace, king, queen, and jack, and the suits are spades, hearts, diamonds, and clubs. And you have to arrange those 16 cards in a square so that in every row and every column, there is exactly one of each suit and exactly one of each type. So there's one king in every row and column, there's one heart in every row and column. And sort of intrinsic in this puzzle, because you're dealing with physical cards, you can't have any repetitions of pairs. So you can't have 2 kings of hearts, for example. Each pair occurs exactly once. So this can be done. There's one solution there. There's plenty of others. After a while, we need a harder challenge. And just such a harder challenge arose in the court of Imperial Russia under Catherine the Great. People were going mad, trying to solve the 36 officers problem. And this is exactly like the card problem, but just for 6. You have here 36 army officers, and they're split into 6 regiments and 6 ranks. So in each regiment, there's one of each of 6 ranks. And you have to arrange them in a square so that in every row and in every column, there's exactly one of each regiment and exactly one of each rank, with no pair being repeated. So every pair occurs exactly once. You have the general from regiment 1 in exactly one place. So this problem, much harder than the 4x4 one. And in fact, no one could do it. Catherine the Great couldn't do it. Empress Regnant of all Russia could not do it. So she asked a passing mathematician who was visiting Petersburg at the time, can you help me? And luckily for her, the passing mathematician was Leonhard Euler. And he's quite a good mathematician. You want him on your team. But he couldn't do it either, right? So when Euler can't do something, we pay attention. He couldn't do it. Well, of course, he will immediately have realised these two questions are the same kind of problem. And actually, the structure that they are both asking us to find is what Euler called a Greco-Latin square. So in a Latin square, you've got one kind of object. We see Latin squares quite often because Sudoku grids are Latin squares, where they have the numbers 1 to 9 exactly once in each row and in each column. In this case, you've got 2 things, so the suits and the types, or the ranks and the regiments. So when he was drawing them, he would label one with Greek letters and one with Latin letters, so Greco-Roman. We don't tend to call them lots of different names nowadays, but I'll stick with what he called. So the question becomes, can you find a Greco-Latin square of order 6, a 6 by 6 one? You can do it if it's order 4. Euler couldn't do it for order 6. If you play around a bit and see what you can manage to do, you quickly will see it's impossible to do it for size 2, order 2. But Euler managed to show you can do it when you've got an odd number, the square is odd size, so 3 by 3, 5 by 5, and you can do it when you've got a multiple of 4. So this is the sort of smallest example of that. But what are the numbers that are left? They're ones that are even but not divisible by 4. Right, so they're 2 more than a multiple of 4. 2 is 2, and 6, the 36 officers problem, 10, 14, and so on. And Euler conjectured that that these Greco-Latin squares exist for all orders except for 2, 6, 10, 14, and so on. And when Euler conjectures something, you believe it because it's Euler. So it was a big surprise. I think it's safe to press the next slide now. Big surprise. In 1959, 3 mathematicians found order 10 Greco-Latin squares. And this is a huge shock. It was on the cover of Scientific American in November 1959. Very exciting. And, big surprise. One of the very few times that Euler made a mistake, failed at something. So this emblem of failure, even one of our greatest geniuses, was the perfect choice for Georges Perec when he wrote Life a User's Manual in the 1970s. So this book, again, I'm stalling for time before I press the next slide. So this book, which you'll see a picture of the cover in a moment, it was set in a Parisian apartment block with 100 rooms in a 10 by 10 array. One of the themes of this book is failure. There are characters that have missions that they're trying to accomplish and they die before they can finish, and all sorts of things going on in the book. The chapters of the book, each chapter is set in a different room in this apartment block. And every chapter has a unique flavour given to it by lists of 10 things that Perec was using. So it might be colours or types of fabric. And he used the Greco-Latin square structure to ensure that every combination occurred in exactly one chapter. So exactly one chapter would have red velvet in it. One chapter would have green satin, right? Something like this. So every chapter has its unique flavour. And there's more structure as well in the book. If you've got a little square, 10 by 10 square of rooms, how do you know which room your next chapter will be set in? Well, the order follows a knight's tour of a 10 by 10 chessboard, which is very nice. But remember, this is a book about failure. The night story is not completed. The book only has 99 chapters. And Perec had a very fun excuse for this. He blames the little girl on pages 295 and 394. There's the cover of the book. So yeah, fantastic use of this structure and just really pertinent to the theme of the book. Okay, so we've got a little bit of time, 10 or so minutes. I want to move on to another way that mathematics can make itself felt in literature. So structure, absolutely at the heart of things. But also, you know, when we've built the foundations of our piece of literature, then we have to decorate our house. We have to furnish the rooms. We have to populate it with characters. At each point, we can reach for imagery and metaphor. And if we enjoy mathematics, maybe we reach for something mathematical. But even the most elemental forms of story have mathematical symbolism in the form of numbers. Fairy tales are full of numbers, and often the same numbers. Here is just some three examples. Goldilocks meets 3 bears. Snow White meets 7 dwarves. There are 12 dancing princesses going through the woods for their clandestine all-night dancing. 3 in particular just is everywhere in fairy tales. There are 3 bears. There are 3 billy goats gruff. There are 3 little pigs. You always get 3 wishes from one of the 3 good fairies. 3, 3, 3. And mathematically speaking, I think there's a very good reason for this. If you think about, so let's imagine a classic fairy tale. 3 brothers go on a quest. That's a classic plot for a fairy tale. We all know what's going to happen. If you've read enough fairy tales, you already know what will happen in this story, barring the details. So the first brother, who's very arrogant, goes on the quest and he fails. That's 1 data point. We don't know, not very much information. There he is, an isolated data point. Then the second brother goes on the quest. He's also very arrogant. He fails. That's a 2nd data point. If we have 2 points, we can make a line. If we have a line, we have a direction of travel, we know what to expect. Now the 3rd, overlooked, humble youngest brother goes on the quest. He succeeds. So we're surprised. We're surprised by this. And in mathematics, you know, what's happening geometrically is 2 points make a boring old line, but 3 is the smallest number of points we need to go up a whole other dimension and make a shape, a triangle. And in the story, 3 is the smallest number of repetitions we need to first set up an expectation and then subvert it. Right? So that's why 3, I think, is so important in narrative, and fairy tales in particular being the most simple stories use a lot of 3s. But of course, we can get more sophisticated if we want to. Let me just mention 2 authors very quickly. There are many, many authors who just clearly enjoy mathematical ideas. It comes out in their writing. George Eliot, I'd say, a bit more than that's Tolstoy, a bit more than Tolstoy. But Tolstoy has some very interesting ideas and in War and Peace, for example, he uses calculus as a metaphor for the whole of human history. He says, just as calculus in mathematics helped us to understand continuous processes and sort of get round things like the paradox of Achilles and the tortoise, which is only a paradox because we're trying to break up time into discrete segments when really it's continuous. We should do the same, think the same about human history. So it's not about 1 or 2 or a few individuals. You know, it's not about Napoleon. Perhaps he's not a great fan of Napoleon. Spoiler alert. You know, it's not about 1 or 2 people. It's not about the great men. It's about every infinitesimally small, you know, decision made by all of the human beings. And the whole sweep of human history is best understood by doing something like calculus, says Tolstoy. It's quite interesting. George Eliot loves mathematics. She studied it in her spare time. She went to geometry lectures. She felt mathematics to be a solace in difficult times. There's a letter from her to some friends of hers where she was explaining how she was getting over a kind of very stressful time. And she said, so every day this is her recipe for happiness, which I strongly recommend. So she says, I play the piano, I read Voltaire, go for a walk, and I do a bit of mathematics. That's what a lovely day. And that feeling of hers, I mean, there's lots of stuff we could say about her books, but that feeling that mathematics consoles you comes out even in her first novel, Adam Bede. He's mourning the loss of his father. He's struggling to find his equilibrium again. And he consoles himself by saying, you know, the square of 4 is 16. That's true whether a man's sad or whether he's happy. These eternal truths in mathematics will always be there. And that's something I can kind of hold on to. So in her writing, you hear mathematics coming out. And Mignon is right, Moby Dick is full of mathematics. But you have to read my book if you want to find out. Occasionally, a bit of mathematics catches the public imagination. And you get things that are just so exciting and all-consuming new ideas that they escape into the wider consciousness. One example of this, Oscar Wilde references the fourth dimension when he's writing about ghosts. How does a ghost walk through walls? Well, they just nip into the fourth dimension, walk through the wall in a different dimension, and then come out the other side. So this is in his little story, The Canterville Ghost. But why is Oscar Wilde suddenly talking about the fourth dimension? Well, because everyone was talking about the fourth dimension. People were referencing it in writing. Of course, all the mathematicians were talking about it, but it made its way out of the bounds of mathematics. So you get people like Proust mentioning the fourth dimension. It talks about a church that exists both in the spatial 3 dimensions and in the temporal 4th dimension. And it's a 4-dimensional object that exists through time. So that's very interesting. That's sort of happening at the end of the 19th century. And I thought, well, what's a more recent example of this, where an idea from mathematics is so exciting? I mean, they're all exciting, but particularly exciting that it kind of escapes its bounds and appears in popular culture. So I'll show you one of these ideas. Not sure what the next slide's going to do. Well, let's see. Okay, right. Fractals. This is just to finish off in the last few minutes. So fractals really had a big vogue, let's say, in the late 1980s, early 1990s. So all student dormitories by law at that time had a picture of the Mandelbrot set on their walls, possibly even a magic eye version that you had to unfocus your eyes to, you know, if you're as old as me, I remember those. Fractals suddenly became super exciting and they were everywhere. You'd see them on people's t-shirts and all this. Why has that happened? Why did that happen then? Well, really, it's only, I drew one for you, but it's hiding under here. I'm sorry. I made a little fractal fern for you. Just imagine the rest of it. It really, as this kind of little passage, a quote from Arcadia alludes to, fractals and studying them really only became possible when computers were good enough to do the many, many iterations that are required to produce the outcome of what you're trying to do. So Tom Stoppard, I had to mention him because he's fantastic, and you know, all of his stuff has so much mathematics in. Arcadia is just a joy from beginning to end, but it's got all sorts of mathematical allusions in it. It's set in 1809 and in the present day, or the then present day, and in the part that's the beginning of the 19th century features this wonderful young woman, Thomasina Coverley, who he has said is not supposed to be Ada Lovelace, although there's stuff about Lord Byron in the book, and anyway, we must believe it. It's not Ada Lovelace. However, she is a young aristocratic woman who is extremely good at mathematics, and she is trying to. She says, "Look, if we can have a curve that's like a bell, and the bell curve, why can't we have a curve like a bluebell?" And she comes up with this idea of how to create the geometry of irregular forms, the forms of nature. And she says, you know, I've found a wonderful method of doing this. All the forms of nature must give up their secrets and draw themselves. And we're led to believe she's talking about fractals, but she can't make it work because she hasn't got a computer. Then there's a nice little joke about Fermat's last theorem. This margin being too mean for my purpose, the reader must look elsewhere for the new geometry of irregular forms by Thomasina Coverley. Computers make fractals possible. I mean, there were a few examples of fractal type things before computers. The Koch snowflake curve was, someone will tell me, 1904, I think. But until we had computers, we couldn't really see the full effect of them. And so what are fractals? What are fractals? They're made by iteration, by repeating processes over and over and over again. In theory, infinitely often. but then we can get a good approximation with a machine. And they have this kind of self-similarity property to them, that within the big design, there are smaller versions of that self-same design. And this is what a lot of things in nature look like. So fractals can help us see things in nature. There's another book that talks about fractals, and it's Jurassic Park. When I say it talks about fractals, it doesn't talk about fractals. What it does is talk about chaos theory. So if you've seen the film Jurassic Park, you will see someone who looks very like a typical mathematician. Don't know why you're laughing. Jeff Goldblum plays the mathematician Ian Malcolm, or a chaologist, I think he calls himself. And there's a lot of talk about chaos theory. And essentially, the message of Jurassic Park is that chaos theory tells us that if a system is sufficiently complex, then you cannot control it. You lose the ability to predict it, kind of like the weather. As an example, if you try and make a dinosaur theme park, you may, because of chaos theory, end up being eaten by a velociraptor. So this is very, warning. Make sure you're good at mathematics before you attempt anything like this. So that's one of the themes of the book. But the book itself has this extra little bonus. It illustrates this idea of systems that get more complicated than we can predict, with some interesting diagrams that appear at the beginning of each of the sections of the book. So the sections, there are 7 of them. That's not one of those magic numbers. There are 7 sections. They're called iterations, which gives us a clue. And there's a little diagram that gradually grows more complicated that appears at the beginning of each of these sections. And it's a very, very simple process that makes it. You get a piece of paper, a strip of paper, fold it in half, unfold it. You've got a little bend there. If you then do it again, fold it twice, unfold, got some more bends appearing, and you keep going. So this is 3 folds, this is 4 folds. You start to get this pattern of, the sort of pathways, right angles appearing. But it's a very simple idea, and you sort of feel like, I ought to be able to write down some sort of equation that would tell me which direction the bend is going to go next at any point. It shouldn't be too hard to do. So at some point your paper gets too mangled to carry on, and so you can tell a computer to do this for you. All you have to do is at each stage replace little straight line segments by a bent line, and you just change the scale a bit, but that's basically what you're doing. You set a computer doing this, and this is what the pictures are in Jurassic Park. So the first iteration is this. So this is a few out. Here's the first iteration, which is actually step 4. Then the second, then the third. It's getting more complicated. And I suspect, I was going to show you 4, 5, 6, and 7, but I expect it will all just appear in one go. Let's see if it does. Okay, this is the 7th iteration in the book. And by this point, you can see this is incredibly complex. And this, if we were to do it infinitely many times, is indeed a fractal. You can see the whole shape appears in smaller sizes throughout it. It's a lovely design, and it's a perfect illustration of the fact that you can start with something that seems so simple and end up with something you could never have predicted. As a bonus, given this is a book about scaly creatures with big teeth, this is called the dragon curve. Which is nice. So this just is kind of an illustration of the fact that ideas from mathematics can really chime, and then they're going to appear in literature. So I hope, I'm going to stop here, but I hope I'd have shown you that knowing a little bit about the mathematics behind literature can help us, 1, do fun mathematics, and 2, enjoy the greatest works of literature that we already love, enjoy them even a little bit more. So I will stop there. Thank you very much.
There's some questions.
Would you like to say something about Lewis Carroll, who's a mathematician and an author?
Yes, indeed. Indeed, you will. Yes. So Lewis Carroll, I think the way his love of mathematics shows himself in his writing is that essentially everything he does is a giant proof by contradiction. In that, for example, he says, okay, if you were able to grow and shrink by drinking potions and eating things, then it would be possible to swim in a lake of your own tears. Right? And that's exactly what happens to Alice at the beginning of Alice in Wonderland. And there's lots of these ideas. If you sort of take things to their logical extremes and see what happens, and this is what mathematicians do all the time. We play with ideas and we stretch them to their limits and we see if they break. If they don't break, maybe we've got a theorem. If they do break, maybe we've got a new kind of structure to explore. And this is what Lewis Carroll does. And there's lots of jokes and things in, you know, in the Alice books and elsewhere. There's when she's talking to the Mock Turtle, right, about going to school, and he says, okay, on the first day we had 12 hours of lessons, and on the next day we had 11 hours of lessons. She says, why is that curious? And he says, well, it's because they lesson every day. Okay, that's say the puns were good. But then so she goes, but wait a minute, that means the next day you had 10 hours, and the next day you had 9 and 8 and 7 and 6. And then what did you do on the 12th day? And he says, that's enough about lessons. But you know, all of these ideas, he's playing with ideas. It's the same thing with his poetry, right? We all know when we read his poems, which are kind of full of nonsense words, but we sort of know what they mean anyway, even though 'twas brillig and the slithy toves did gyre and gimble in the wabe, or whatever it is, you know, we sort of know what that means, even though none of the words are words. And I think that's what he's doing there, is he's sort of piggybacking on the structure of language and the structure of words to make us feel that we have a meaning, we can grasp the meaning. So it's all very mathematical, but you know, I think it's all about logic and following logic, even if it's not the usual logic, to its conclusions. That's a long answer, sorry. Yeah.
I read somewhere that the English word chortle came into existence from the Jabberwocky.
Well, if so, then that's very cool, and it just shows what you can do with mathematical thinking.
The question? Is there a question that?
Scratch my head.
I have that effect on people.
Just wanted to add something. I mean, not a question. There is also an interesting play written by Samuel Beckett, which is called Quats. And it is written for television, as far as I know, television play. Basically, also relying on a geometrical object in this, you know, stage with square, and then relying on certain movements of the players with music and the light. This was also an interesting idea, using the geometrical object to implement some play.
Yeah, and I mean, you could think about the kind of narrative, and there's a geometry involved, especially obviously in theatre. You can see it physically in front of you, but sort of thinking about self-similarity and nesting and things, there's a way in which, if you take something like, you know, in Macbeth, no, in Hamlet, where there's a play within a play, right? So there's a play that you're watching a play, and inside that there is a play that's going on that the characters are themselves watching. And it's sort of, if you add a dimension for every piece of narrative distance, you've kind of got a hypercube happening, and the mini theatre set within the bigger theatre set is like a cube within a bigger cube. So, you know, there's some fun ideas to be had if you think about narrative distance in that way of multi-dimensional narrative.
Any other questions? Maybe I did have one question, or maybe it, I'm not, that the book Luminary, you were referring to, the goal was 4096
Yeah.
something? Or?
Yeah.
I wonder, I mean, I feel like if she was really trying to illustrate the sum formula, it would have made it 4095.
Well, yeah, this is, so why isn't it 2 to the 12 minus 1 is the question.
Right.
My feeling is that might, then you might not have spotted it. Like if I see 4095, I don't necessarily think, oh, it's one less. I should, of course, we all immediately think it's 2 to 12 minus 1, but maybe she wanted to give a more plain hint that I don't know if it's harder to spot, I think, 4095 as a potentially interesting. So maybe that's the reason. But yeah, you know, I'd accept either answer. My Booker Prize winning novelist.
Okay, great. Well, if there are no more questions, let's thank Sarah again for a wonderful. about to invite everybody to the reception outside. Let me make sure it's there.